All right. We are looking. We're looking good, I believe. Yeah, let's just go ahead and hop right into it. So, welcome back to the math library. I know it is. It's not OpenGL. Um, I'm feeling a tad burnt out right now, just from the end of school. Sorry, my voice is raspy. Yeah, my semester just ended, so I'm feeling a little burnt out right now. So I will be working on that very soon, though. Once I have the time to sit down, write a good chunk of code for the OpenGL stuff, and actually do something in it, which I'm thinking of what I want to do, and I will. Sorry. And I will let you guys know when that will be coming out. But anyway, today we're going to be continuing on with the graphs, and we're going to be looking at our first kind of advanced algorithm beyond our traversals. So we already have the DFS as our traversal algorithm, and now we're going to want to integrate some other algorithms. So today we're going to be looking at the shortest path problem. So how do you get from one node to another? So let's say we had a graph, or I'll just number these as they would be in the index, or as their indices. So 0, 1, 2, 3, 4, 5, and 6. And then we have a bunch of edges here. I'll make these directed for now. Alright, so let's say these are our edges, and then we'll assign some weights to them. So we'll do 6, 5, 3, 2, 7, 11, 15, 2, 1, 6, and then 3. So if we wanted to, let's say that a good application of graphs is navigation. So where you represent each kind of place with a node. So if we had cities as nodes, and we wanted to find the fastest way from city 0 to city 6, well, we could kind of look here. All right, so this is just me looking at this. I'm going to say that the shortest path is 0 to 3, 3 to 2, 2 to 5, 5 to 4, and 4 to 6. Now, how did I come up with that? Well, this was honestly a bit of a guess, but I believe it's right because we look at this and it's 7, 9, 4, 13. 7, 9, 10, 13. 13, yeah. And that seems to be the smallest weight because we're going to have to go through one of these three edges to get to a 4, to get to a 5, or a 4 to get to a 6. One of these three edges here, and 15 already is just larger than that weight, so that would be longer. And I did kind of forget to say this, but the weight of a path is just the sum of the weight of the edges that we take along the path. And 13 and 11 is pretty big, and if we add anything else here, we would get above a 13. So that would be already the longest. So like that's just a guess, but I'm pretty sure that's correct. Yeah. So Dijkstra's algorithm is it's a greedy algorithm. So we're going to be using a greedy kind of template to solve this. That will find the shortest path tree. Now the shortest path tree is essentially it originates at a source, and if you go along the tree, you will find the shortest path to any node. So in this case, another shortest, let's say we wanted to find the shortest path from 0 to 1. Well, that's just 0 to 1 weight of 6 because there's no other way to get to 1. 0 to 3 is going to be 5 and a 0 to 3 is just a 5, and we already found that. 0 to 2, look at this, it's already along that same path. So we're kind of seeing here, okay, well, we found the shortest path to 6, but that also includes the shortest path from 0 to 3, 0 to 2, 0 to 5, 0 to 4, and 0 to 6. So you kind of start seeing this structure here where we have our smaller problems where we want to find the shortest path between 2 nodes, and we can then combine those shortest paths to make the shortest paths tree. And this actually turns out to be the shortest path tree, I believe, for this example. It's 0 to 1, 3, 2, 5, 4, and then 6. And just as a proof, I mean, try and find the shortest path from 0 to 2. I mean, it's pretty obvious. 5 and 2 is greater than 6 and 7, or 6, 3, 2. We already know that. So we have just 5 and 2 is 7. 6 plus 7 would be 13. 6 plus 3 plus 2 would be 11, so they're all greater than 7. Now, algorithmically, how does this work out? Well, like I said, it's going to be a greedy template here. So the loop here, we're obviously going to loop out here, but we can't kind of just say, okay, find every single path here, and then we're just going to look at the shortest paths. That would be too long. You can apply more of a algorithmic approach to this. And it turns out that the best way to do this would be just at each step or at each iteration of the loop, you're going to choose the edge, the current edge that is present and has the smallest weight. So, for example, let me erase these. Let me erase all these markings here, and I will start with our empty graph again. So let's say we called Dijkstra and we have to start at a source. So let's start at source. The source is 0. So we start over here. That's our source. So we look at our 2 edges, 6 and 5. These are our 2 viable edges right now. So 6 and 5, we have we find the shortest path, which is just a 5. So the 5 will be the shortest path here. And I'll circle that. So therefore, we will take the shortest path or we will mark this edge here, and then we will go to 3. We see the shortest path is now 2 because our present edges are we have our present edges as 6 and 2. Those are 6, 2, and 11 here. Our present edges are this one, and this one. And I'll just mark this as before. So our present edge is 6, 2, and 11. We see that the smallest weight is the 2. So then we go to vertex 2. And we follow the same process. Except this time, we're going to... Oh, wait, sorry. That's wrong. That is actually incorrect. We don't take the 2 as the shortest weight, because we are essentially going to increment this 2 by the weight it took to get to the 3. So we mark the 3 with a weight of 5. So I'll mark the weights here with purple. So obviously the source will have 0. The 3 will have a weight of 5. So the current weights we have now are 6, a 5 plus a 2, and a 5 plus an 11. So we have a 6, a 7, and a 16. So we obviously will take the 6 as the smallest weight. And then we will go to 1. So I'll circle the 1 here. And this will now have a weight of 6, because that's the weight it took to get from 0 to 1. So now we update all the weights, or all the edges coming out of 1 with this weight. So 6 plus 3, and 6 plus 7. So now we have our weights as a 7, because these edges are still there. So we have a 7, a 16, a 9 from here and a 13 from there. So we take the 7 edge. This edge right here. All right, then we go to 2. Mark it with its lowest weight, which is a 7. And then we increment all the next weight. So 7 plus 2, 7 plus 15. So now we have our weights as 13, 9. Well, we can then since we have visited these other edges, we can now discard any or since we've visited vertex 2 and 3, we can discard any of these other these edges here. So I will discard them with that. So discard those two. So now our present edges become, we still have the 16, the 5 plus 11, which is 16. 7 plus 15 is going to be 22, and the 7 plus 2 is a 9. So obviously we're going to take the 9 here. Here, let me just circle the 2 actually. So we take the 9, since that's the lowest weight, move over to vertex 5, and mark it with a weight of 9. And then we increment all the weights of these edges, 9 plus 1, 9 plus 6. So now our present edges, we have 5 plus 11, 7 plus 15, 9 plus 1, 9 plus 6. Our lowest weight is going to be the 9 plus 1, which gives us 10. So we get that. Move to 4, or make that circle a little cleaner. So then we move to vertex 4. We can discard this edge here, since we moved to it. So we're at vertex 4, and this has a weight of 10. So then we increment the 3, so 10 plus 3 gives us 13, 9 plus 6 gives us 15. So we're going to take the 10 plus 3, and that will get us to vertex 6. So we go to vertex 6, and then we discard the 9 plus 6 edge. So once all the vertices have been visited, now we have our shortest paths tree. And I'll just trace this out here with a red pen. So we took the 6, so 0 to 1. Well, first we went 0 to 3. Here, let me just retrace this as we did it. So the first edge we took was 0 to 3. Then we did 0 to 1. Then we did 3 to 2. Then we did 2 to 5. Then 5 to 4. And then 4 to 6. So you get the shortest paths tree from tracing out the lightest edges that we chose. So yeah, that's how that essentially works out, which is pretty good. Hold on, let me just make sure that this is all transmitting properly. We don't have any messages, so we're all good. Good shit. Alright, so yeah, that's going to be essentially how we do it. Something you might compare this to would be breadth first search, which we have not looked at actually, and I don't know if we will. But essentially, the principle behind breadth first search is we use a queue. So we take we take a vertex. We instead of using a stack, so we wanted to discover the closest vertices first rather than go as deep as possible first, which is in depth first search, or DFS, which we looked at last time. So with breadth first, we look at the closest vertices first, and that's what we did here. We looked at which vertices were closest to us. Except this in Dijkstra, we're not using a first in first out queue. We're not going to use a queue structure. We're going to be using something else to sort through which vertices we want to find first. And the thing I was comparing were the weights. So we're going to use some kind of queue that will allow us to sort nodes. And it turns out that we have one, which is the priority queue, or the minimum heap. And we have actually written the code for the minimum heap in a previous programming challenge, so I'm going to use those files today. But we're going to make some modifications to them. But the purpose of that is so that we can kind of just have a tree structure that will always have the smallest weighted element at the top, and that smallest weighted element will be the smallest weighted node we have, and you can kind of think of them as edges. So 6, 3, 2, 2, whatever. Sorry, the 6, the 5, the 7. Those are going to be our weights here. So let me kind of diagram how we're going to do that here. So I should have copied this graph, but I'll just copy this graph either way, and I'll erase this stuff. Oh, there we go. Sorry about this. This is just quicker than redrawing the whole thing. I think it is. Maybe it's not. That was a 2. Come on. Oh, come on. There we go. All right, I just need to make sure that this stuff is going through properly. All right, we're good. We're good now. Perfect. All right, so let's start again now. But this time, let's think about it as a minimum queue. So if we initialize all the weights as infinity, so if we use the nodes in the graph as the nodes in the minimum queue and initialize their weights as infinity, this will give us the proper structure that we want, where the source has a weight of 0, so it will be the lightest edge or the lightest node. So we will pop that first. So when we take the 0 here, that's our first thing. And then what we're going to do is we're going to find the smallest edge, which is the 5 here. And what did we do when we did that? We went to the 3, and we set the weight of the 3 as 5. So we cross out this edge, decrease its weight to 5, and then in the minimum queue, this would equate to calling up heap on it with its new key. So we're going to resort the heap with this new key. So we have a 5, and then we would also decrease this key to 6. So since we found an edge to it with weight 6, so 0 to 5, or a path to it with weight 6. 0 to 3 is 5, and 0 to 1 is 6. So the top of the heap would now be the edge, or would now be vertex 3, since it has a weight of 5. Now we pop the 5, we decrease the weights of the other edges. So we go 3 to 2. This has a weight of 2, so we do 5 plus 2 is 7. And then we do the same thing for the 4. So 5 plus 11 is 16. Or let me do this over here. So now 4 has a weight of 16, and 5 and 6 are still undiscovered. So now the smallest weight, or the top of the heap, will be vertex 1, since it has a weight of 6. So we're going to go to vertex 1. Sorry, let me just... Oops. There we go. So vertex 1, we're going to decrease the weights of the other edges. So we look at this edge from 1 to 3. Well, we see 3 is not in the queue, so we don't need to touch it. Now, 1 to 2, this will give us a weight of 6 plus 7 is 13. However, 13 is greater than 7, so we don't need to touch the key of 2. So we just leave that alone. Now, we've done 6. So we set the parent of 3 as 0, and the parent of 1 is also 0. Now the top of the queue will be 7, or vertex 2. So we set the parent of 2 to 3, and then we update the edges. So the weight from 2 to 5 is 2, so it would be set 7 plus 2, which is 9, is less than infinity. So this will become a 9. And then 7 plus 15 is 22. However, that is greater than 16, so we don't touch the 16 with the key of 4, which is 16. All right, so we have we visited the 2. So now we have in the queue left, we have a 9 and a 16 and an infinity. So we select the weight with 9, or the vertex with weight 9, which will be 5. So we go to 5, set the parent of 5 to 2. And then we update the edges. So let's look at our edges here. We have 9 plus 1 is 10. 10 is less than 16. So we update the key of 4. And then 9 plus 6 is 15. Update the key of 6. So we now have a 10 and a 15 in the queue. 10 is the smallest. So 5 will point to 4. We will pop the 4. So we're visiting the 4. And then we will update the weights, and the only edge of 4 is going to be the edge to 6. So 10 plus 3 is 13. Update the weight again of 16, or of vertex 6. So we do that. And then the smallest on the queue will be the only one left, which is the 6. Visit the 6, set its parent to 4, and we are done. And we have our shortest path tree. So it's as simple as that. Okay, so let's write this code now. So that's in essence Dijkstra's algorithm. It seems daunting, but when we write the code, it's actually somewhat simple because we already have a minimum queue, which is awesome. Didn't even think about this when I wrote that code, but it so happens that we have it, so that's cool. Okay, so let's go into Visual Studio Code, and we're going to be in we first want to add the minimum heap files, which can be accessed on GitHub. I put them in the C Mathematics repository already, so you can access them there. But if you want to write them from as they were, then go to the YouTube challenges repository. I link this down below. And it's challenge 23, generic min heaps. Alright, so we will hop into minheap.h. Now, the reason why we need to modify the minimum heap code is because, let me just turn this music down a bit. I bet it's extremely loud. So the reason why we need to touch the code in minimum heap is when we set the keys, or when we change the keys, we want to call upheap. However, upheap looks for an index. So if upheap looks for an index and we don't necessarily know what the index of the node in the heap is, because once again, if you don't know what a minimum heap is, it's essentially a binary tree that we represent using an array. It's a balanced binary tree that we represent using an array, and yeah, so we represent it with an array here, the heap. And so we want to call upheap, and we will upheap the node at index IDX here. Now in order to find this index, we need to kind of keep track of it. And the only way this index would change is if we modify it. So we can kind of attach an index map to the minimum heap. So once we have added all of our nodes into the heap, we can attach an index map, which will just keep track of the indices of each node. And each node will where once again each node is just represented as an index. So this is going to be kind of weird. So we're having two arrays here. We have an array of nodes, which is in our graph structure right here. It's not really an array. We just have it, we just call them 0, 1, 2 all the way up to n. Now in our minimum heap, we're going to have another array with the same nodes, except they're going to be storing weights as well. So when we call index, or when we find an index, that index will be different from its node value, just because of the way the minimum heap algorithm sorts nodes. So we're going to want to have a separate array in here. So let me find my code. So in minheap.h, we're going to have an integer array. So integer pointer index map. So this map will essentially store. So in each index of the index map, or in each slot of the index map, here I'm going to draw this out actually, because this will be a lot easier to explain if it's drawn out. So initially, if we have our stuff here, and so we need 7 slots. So 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. Good. So these are our 7 slots of our index map. And let's also have our heap as an array. So let's have another 7 here. So at index 0 in the index map, this will store the index of node 0 in the heap, and so on and so forth. 3, 4, 5, 6. So initially, we start with our source at index 0. So vertex 0 starts over here. And I will actually, let me just diagram this a little better. So we start with index or vertex 0 in the first slot, and it has a weight of 0. And all the others, so 1, 2, 3, 4, 5, and 6 have weights of infinity. So the index map, when we generate it, will be vertex 0 is at index 0. Vertex 1 is at index 1. Vertex 2 is at index 2. Vertex 3 is at index 3. I'm just looking at these here. Vertex 4 is at 4. 5 is at 5. And 6 is at index 6. And that's just now. When we pass our first iteration, we see that this will be decreased to 5. So the key on 3 will be decreased to 5. And let's just say this will swap with 1. So 3 and 5 will move over to the first one. And 1 and vertex 1 and with weight infinity will move over to 3. So in the index map, this will just swap the indices here. So vertex 3 is now at index 1, and vertex 1 is at index 3. Just like that. So that's kind of how this is going to work. And I'll just do another one. Vertex 2, that we just update the key to 6, and it should be where it is. So it stays there. Then we update vertex, oh wait, sorry. This should be vertex 1 updates to 6. So vertex 1 will move up, vertex 2 will move down, and we will update the indices accordingly. So vertex 1 is now at index 2, and vertex 2 is now at index 3. Now our next iteration, once we have popped, so we pop the 0, we pop the 3, we pop the 1. Now we go to 2, which has an updated weight of 7. So the 7, so this will stay where it is, and so on and so forth, kind of. So when we pop the 2, we discover a 5 and a 4 and a 5. So 4 will have weight 16, and 5 will have a weight of 9. So we need to swap these. This isn't actually how it does, like this index swapping isn't actually how it does it, but this, I'm just trying to explain the index map here. So now index 4 will be at index 5, and index 5 will be at index 4, and so on and so forth, until we get to 6 and pop everything out of the heap. And once this heap is empty, then we know we have finished Dijkstra. So now, when we look at minimum heap, we have an integer point and an integer array as the index map, where each slot in the, so the 0th slot in the index map corresponds to the index of vertex 0 in the heap, which is just an array. Okay? So that's kind of how that's how we're going to work this out. So we're also going to want to, just for generalization, so we can maybe use an index map in other applications, we're going to want to have an index function here, because these are just void pointers. And the minimum heap stores an array of void pointers. It doesn't know that we have an integer there, so we're going to want to have a function, a callback function that returns an integer called index function, takes in a void pointer v, and it will return the index corresponding to v. So for our nodes, the integer this function returns will simply just be the index of the node. So for vertex 1, it will return 1. For vertex 6, it will return 6. All right, and then we have 2 new functions to create here. Attach map and update index. So they both return void. So void mHeap attach index map, we're going to pass in the minimum heap pointer to attach it to, and then they call back for the function. So int index func, so this is the callback here, and it takes in a parameter of a void pointer, which is just the same thing as this up here. So you can essentially just copy this member of the structure into the parameter here. And then we will have a void mHeap update index, pass in a minHeap heap, and we will be updating the index of void pointer e with index idx. Alright, so let's copy these 2 signatures and we will put them in minheap.c. Alright, so for attach index map, we're going to have a check here to determine if there already is an index map attached. So if heap dot index map, then we're just going to free the existing map. So free heap dot index map. Now we're going to allocate memory. So heap dot index map is equal to malloc heap dot size times the size of an integer. So we're just going to allocate one slot in the array for each element. And then heap.index function is equal to index function. Now for update index, we're going to have if heap.index map and heap.index function and e, then heap.index map at, now the index, so these are just a check here just to make sure the memory was actually allocated. Now we're going to go into the index map and we're going to set it to the index. Set it to the value that we pass in here. Now the index that we want to set at is going to be, we can get this using the function, the callback. So heap dot index function and pass in the element, which is e, and set this equal to idx. So I know I said index maybe 30 million times, and you're probably super confused. So this line of code here is very telling. So we go into the index map. This just stores the indices. And in the index map, we want to find the corresponding index of the element that we pass in. So of element e, using the index function. That's just the callback that we pass in attach index map. And then we want to set the new index in, so the index of this element e in the heap, we want to set that index value as the value in the index map for this element. So, like I said, we're updating the indices in the index map based on the index of the element in the heap. And I did forget something. In minheap we need, for the attach index map, we need to have an integer n for the size of the array. And then over here we're going to say int n, and then if n is equal to 0, so if not n, then just set n is equal to heap.size. Because we're gonna have this where we're gonna update, or where we add something, and we may want to input that to the heap or into the index map as well. So we will just have oh wait, I completely screwed this up. I didn't even complete attach index map. So then we should call malloc using n times the size of an integer. So if we pass in n as 0, or if n is equal to -1 rather, or no, if not n, then we set n to the heap size. Now I did forget this. So after we set the index function callback, we need to iterate through the existing elements and input them into the index map. So for integer I is equal to 1, remember this is a heap, so we start at index 1, since we have a padding at 0 just for easier counting. So I is equal to 1, I is less than heap.size, I++, and then we're simply going to use this same update index here. So we're going to use the same call here. So heap.indexMap at indexFunc, and we're going to call indexFunc with the element heap.heap at I, and then set this equal to I. So this is also very telling of how this index map will work. We're going to set the index in the map of the element at index I, or at I in the heap to I. So in the index map, if the element is at index I in the heap, the value corresponding to that element in the index map will be 1. Will be I mean. Alright, now next thing we need to do is in swap elements. This is one of the places that we're updating indices, so we need to call mheap update index, pass in heap. The element to update will be heap.heap at I1, and the new index of at I1 will just be I1. And then mheap update index, heap dot heap at I2 and set this to I2 just as we did with I1. All right, and whenever we call swap elements, this will automatically update the indices. So whenever we call upheap, which is right here, which is what we will actually do, we're going to call upheap in Dijkstra. This will automatically update the indices in the index map, which is pretty good. All right, next you want to go into add, which is right here. And all we're going to do is, after we set the value at heap.size, we're going to say mheap update index heap. The value to update will be the value that we added, and then the index will be heap.size. And then whenever we call upheap, this will just, calling upheap will once again update the indices of the elements if we swap them. And then in pop, what we're going to want to do is set mheap update index. We want to set the index of the element that we're popping to -1. Just so we can kind of say, okay, it's gone. We don't need it anymore. And then the other thing we have to do is once we substitute with the last node, then we need to say mheap update index, passing heap, and heap.heap at 1 with index 1. So we're going to update the node at index 1. We're going to set that its index in the index map to 1 since we just passed it up there. Once again, for the theory behind this, just watch the video if you want. But this is the code that we need to update, and then finally in heap.free, we just need to say if heap.index map, then free heap.index map. All right, so that's all we need to do for minheap.c. Now, the next thing we want to do is we're actually going to start writing Dijkstra. So let's go into graph.h and let's create this our function signature here. So it will return an integer pointer because the simplest way to represent a tree is just by a list of parents. Now, when we did this, we got a shortest path tree that had our kind of traced out like this, and I kept saying set the parent of 4 to 5, set the parent of 2 to 3. And all we're going to be doing there is just use parents, or use an index to keep track of the parents there. So when we set the parent of 1 to 0, what we're doing is in this array here. I don't know, can I paste this? No, I can't. So this is our parent array, or predecessor array. We're returning this, and this will keep track of the parents. So we start out as everything is -1, and then we're going to set the source to 0. So that's just our base case essentially. Not really a base case, but that's just our initial condition. And then when we find our paths, so we see that we find the path 0 to 3, lightest weight is 5. So we set the parent of 3 to 0. Like that. Set the parent of 1 to 0. Then we set the parent of 2 to 3. And then we set the parent of 5 to 2. Set the parent of 4 to 5, and the parent of 6 to 4. And you'll notice that this also allows us to keep track of the nodes that have been finished, or the nodes that we have found the shortest paths to so far. If they're -1, then we haven't found a shortest path yet. It hasn't been popped yet. It hasn't been popped from the minimum heap. So this will be the thing that we return. And if you just trace back through this, so let's say we wanted to find the shortest path to vertex 5, well, we would go in the parent array. All right, so the parent of 5 is 2. So we go from 5 to 2. The parent of 2 is 3, so go to 3. Parent of 3 is 0, go to 0. And the parent of 0 is 0, which is the source, so we're done. So the shortest path from 0 to 5 is 0, 3, 2, 5, which is shown in the tree here, 0, 3, 2, 5. All right, so that's what we're going to be returning. So return integer pointer, and we're just going to call this graph Dijkstra. Sorry about that. Alright, so yeah, this is our signature. It takes in a graph pointer and an integer for the source node, which it's as simple as that. Alright, so let's copy and paste this signature into graph.c at the bottom. So let's start writing the code. So our initialization. We need an array to store the weights. So we'll have an integer pointer d, which is equal to malloc g dot n times the size of an integer. So this is the array that we will be storing the infinities, the 6s, the infinities, the 7s, the 5s, the 10s, the 16s, 13, 15, 9, and 0. That's what we're going to be putting in here. We're also going to have a parent array. So integer p, parent array, sorry, misspoke, is equal to malloc g.n times the size of an integer. This is going to be a return. So we can actually just go ahead and say, at the end, we're going to return p. I'll say predecessor array, because technically it's called, in more technical or in more professional terms, it's called the predecessors rather than the parents, but they're interchangeable. All right, and then we want to have our queue, our minimum heap, our priority queue, whatever the hell you want to call it. So min heap queue is equal to m heap allocate, and it's going to be the now for the function, or sorry, for the comparison. Or what? Sorry, I completely got ahead of myself. Don't do this yet. So for the queue, we need to just determine what to actually store in there, because it wants void pointers. We could do integers, but that'd be a little annoying, but that also wouldn't allow us to compare the weights. So we're going to want to create a structure here. So I'm going to go above here, and I can just do this in the source file because we don't need it in the header file. So we'll have a type def struct, and the name of the structure will be Dijkstra node. And this will have two things. An integer v for the vertex, and then the weight to the vertex as the key. So integer pointer weight, weight to the vertex serves as the key. So this will be the key. Now why to make it a pointer? So we already have an array of weights here. So when we update it in this array, we don't want to update it in both because that'd be hard to find it in the minimum heap. We would have to. I don't even know what. I don't even want to fucking respond to that, Yash. Jesus. Son of a bitch. Oh man. Okay. So yeah, we have our arrays of weights here, and we just want to refer to this rather than looking into the minimum heap to find the weight. So we can just have the Dijkstra nodes point to the minimum weights there, and that's going to make it a little easier for access. And once we update it in here, it will automatically update in the pointer because it just points to the memory which we updated. All right. So we have our Dijkstra node here, and we're going to want to create two methods for it. We're going to have a Dijkstra node pointer return. It's going to be a create Dijkstra node, and this just takes an integer pointer node and an integer pointer weight. So sorry, this is integer node and an integer pointer weight. So we'll just set the value. So Dijkstra node pointer ret is equal to malloc the size of a Dijkstra node. Ret.v is equal to the node that we passed in, and ret.weight is equal to the pointer that we passed in. So return ret. Just like that. Now, since we're putting these in the minimum heap, we're going to need a comparison function. So, we're going to have a return integer. It's going to be a Dijkstra node compare. Pass in a void pointer v1 and a void pointer v2. So this is going to be two. I don't know why I made it this long, but I'm just for general sake. So we will have Dijkstra node pointer n1, which is equal to v1, and Dijkstra node pointer n2, which is equal to v2. These will automatically cast. Then we're going to get the weight. So integer, a pure integer, not a pointer, is equal to integer w1 is equal to the dereference of Dijkstra node. So sorry, we're going to convert. Wait, what am I doing here? I'm sorry. The dereference of n1.weight. And then integer w2 is equal to the dereference of n2.weight. So now that we have the two weights, we can compare them. So if w1 is greater than w2, return 1. Else if w1 is equal to w2, return 0. And then else return -1. So once again, we're comparing these nodes based on their weights, which is what we have over here. We were choosing the lightest node or the lightest edge based on their weights, their keys or that are in the nodes, not the node values, their weights. So we need to compare those. And then, so that will be the queue construction. So in graph Dijkstra, we can initialize our queue. So min heap q is equal to m heap allocate, and the function to compare will be Dijkstra node compare. Let me actually just rename these functions. I actually did not I did not include this. So at the top of graph.h, we need to include lib/minheap.h, and then we should be good. Yeah, all good now. All right, so our initialization steps. So first step is to initialize the source values. So the weight of the source node is 0. That's just a fact. Distance from the source to the source, there is no distance. Or if you even have a cycle there, it won't matter, because that will be greater than 0. If you're already at the node, you don't need to travel to get back to the node. And then we set the parent of the source to the source. And then we want to add this to the heap. So mheap add a reference to q, and the value will be create Dijkstra node. The integer of the node will be source, and the weight will be d plus src. So what is this? Why did I say d plus src? So this is just pointer arithmetic. This gets us the source's weight. We just go source indices into the array, and this will just give us that. So now we're going to add the other nodes. So for integer I is equal to 0, I is less than g.n, I plus plus. So we're going to say if I is equal to source, then continue, because we've already added it. Now, the reason why I'm adding this source first is because it will have a weight of 0. And I don't want to call upheap if I don't have to, because let's say our source was 1, then this would give us a weight of 0 at 1, but a weight of infinity at 0. So we would need to call upheap on 1, which would take some time. So I'm just going to insert the source first, so we don't need to call upheap initially. Alright, and then all we're going to say here is the distance at I is equal to integer max, so the maximum value, and then the predecessor of I is equal to -1, since we have not discovered it yet. And then we're going to add it to the heap. So mheap add reference to q, and the value to add will be create Dijkstra node. The node will be I, and the weight will be d plus I for similar reasons. All right, so that's our initialization. Now we want to attach our index map, but once again we need an index function, and it simply can just be return type integer Dijkstra node index, pass in a void pointer v, and all we're going to do here is just return Dijkstra node pointer, the conversion of v dot v. So we're going to convert the void pointer parameter that we got to a Dijkstra node, and then just get the vertex, and which is our index, as I said before. So then we want to attach this map by calling mheap attach index map, pass in a reference to q, an index function, or Dijkstra node index. All right, now for the main loop. Alright, so this is the main loop. So we're going to be continuously popping nodes from the current heap. So we're going to want to say Dijkstra. We're going to want to have a placeholder. So Dijkstra node current is equal to null. Then while current is equal to mheap current is equal to m heap pop, passing reference to q. So while current has some value, so while there is something to pop, we're going to relax the edges. So what I was saying with, okay, so 6 is less than infinity, that's called relaxing the edges. So once again, if like when we found the weight of 6 to 1, we say that that's less than the current shortest distance. So we relax the edge from infinity to 6. And at 4, when we initially had a weight of 16 and we found a shorter path of weight 10, then we're relaxing the edge from weight 16 to weight 10. But relaxing is dependent, the way we relax is dependent on the adjacency mode. So I will start with the adjacency list, just because it's, I mean, it doesn't matter which one I start with, or I'll start with the adjacency matrix because that's a little easier to look at. So relax edges from the popped node. So if g.adjacency mode, and then I'm going to go into else, because once again, if g.adjacency mode will be true if it has lists, and else it will be false if it has matrices. So we're going to say for int v is equal to 0, v is less than g.n, and v++. So we want to determine if they're we want to determine 3 things, or we want to determine 2 things. If an edge exists from the current value to v, because once again the matrix just has weights for all of the neighbors, or all the possible neighbors, so it will have a value if there is a neighbor. If there exists an edge from v to whatever the index v is, or from the current node to v. So this if statement will be if g.adjacency matrix, g.adjacency matrix at current.v, and then we're going to make sure that the node v has not been discovered yet. So q.index map at v does not equal -1. So once again, we're going to the index map. So we get the index map from the queue and say if it's -1, then we have popped it. And this will be popped in m heap, or it will be set to -1 in m heap pop. And then we want to have one more check here. So if current dot v does not equal v. So this is just a check just to make sure that we don't go to itself, because it will never be less than. So we just want to avoid that. Alright, so if this passes, we know there's an edge that exists from current to v, and v is not finished. Now we're going to determine if the edge, or if there's a smaller path, or a quicker path. Determine if lighter path to v through current. So we're going to say here, if d at v, so if the current weight of vertex v is greater than the current distance to current, so we're going to say the distance to current dot v. So current dot v just gives us the index, the current index, or the index that we popped. So the index of the node. Once again, v has the node number. So if that has a smaller distance plus the weight of the edge from current to v. So plus g dot adjacency matrix from current dot v to v. So if the estimate for our distance to v is greater than the path to D plus the weight from V to sorry, I'm mixing myself up. So let me go into this here. I will diagram this out because once again, words speak louder than written words speak louder than my words, I think. Where's my pen? Oh, it's over here. Alright, so for example, let's look at this step over here. So when we got to 2. So D at 2 is equal to infinity, or integer max, as we set it initially. Let me actually just comment that. The distance to 5, D at 5, is equal to, or the distance to 3, sorry, is 5. And once again, these are the keys. These are these keys here in the heap. That's these values right over here. These are our keys. So these are going to be the weights in the distance array. So D at 3 is 5. And the weight, so G from 3 to 2, is 2. So we're going to want to say, is 5 plus 2, is that less than infinity? And if it is, then we want to update it. Update the weight. Oops, there we go. So that's what this if statement says. If the distance, or if the current estimation for the shortest path to V is greater than a different path, then we just want to set it to the other path, the current path that we're finding. So update weight. So D at V is equal to D at current dot V plus G dot adjacency matrix from current dot V to V, and that's just this value here. And obviously it's a lighter path, so we want to set it as the new approximate. And then, as I said before, we want to keep track of parents, so we're going to set the parent of V to current dot V. And then we want to decrease the key, or call up heap on the new weight. So m heap, up heap, pass in a reference to Q, and say Q.index map at V. So we get the index so the index map at V, so remember V is just an index for a neighbor. This stores the index of the vertex V in the heap. So we want to call up heap from that index in the heap. And that's why this index map is so helpful. And once again, we don't need to update anything in the heap, any keys in the heap, because that just points to this weight which we just updated. Which is cool. And then after else, we're going to say free the current node, because we popped it and we no longer need it, so just free it. And this doesn't affect the graph at all, because free current just frees the memory and the structure. Just these two values here. Now let's write this for the adjacency lists. It'll be very similar, so I'm going to blast through this. So we're going to iterate through all the edges. Edge pointer E is equal to null, then dynamic array, iterator, it is equal to dynamic array iterator, new, passing in g.adjacency lists plus current.v. If you watched, I mean, if when we did DFS, this was the same thing, just iterating through all the edges, just getting the dynamic list for the current node. And then while E is equal to dynamic array iterator next, passing reference to it, while this has a value, so while we find an edge, we're going to say int v is equal to e dot v2. So now v becomes the second vertex on the edge. So it's the same v, just we're getting v a different way. And then we can have a check here. So if q dot index map at v does not equal 1, or does not equal -1, or first we want to determine if v is not equal to current. So if current dot v does not equal v and the vertex v has not been discovered. So once again, current is not v, v is not finished. And we don't need to have this middle check to see if the edge exists because we're just iterating through all the possible edges. So that will, we already know the edge exists because it wouldn't be in the list otherwise. And then in this condition here, we're going to relax the edge. So determine if the lighter path to v through the current. And this check will just be if d dot v, or d at v, is greater than d at current dot v plus e dot weight. So now the weight of the edge is just stored in the edge that we got from the iterator. And then we're going to say d at v is equal to d at current dot v plus e dot weight. So once again, we're just going to update it to the new weight. Set the parent, since we found a shorter path through the parent, or through the predecessor. So p at v is equal to current dot v, and then call up heap on the new weight. So m heap, up heap, reference to q, and q dot index map at v. And that's that. So same sort of stuff, just get the weight a different way. Now after the loop, we're going to do a bit of cleanup. And simply going to be we're just going to call m heap free deep, pass in reference to q, and then free the weight array, which is d. So that's fucking it. That's Dijkstra's algorithm. Pretty cool. So yeah, let me just recap quickly on the index situation because I don't know if I explained it well enough. So the only index, so for most of these arrays, I'm going to say for all the arrays except one, the index of vertex I will be I. That's just how we've done it throughout this structure and in the last video too. The only array where that is not the case, it will be in the heap, because the heap will be sorting the vertices based on their weights. So therefore we attached an index map to the minimum heap so that we could keep track of the index of each node in the minimum heap, and therefore we can get these values here, and this index map will allow us to call up heap on the proper node and determine if that node has been finished, just like that, which is cool. And the index map will has the index map is also proper or normal, where the value at index 0 corresponds to the value for vertex 0. Alright, so yeah, that's Dijkstra's algorithm. Let's run this over here. So I can finally delete the big integer stuff here. Finally figured that shit out. Thank the fucking lords. So let's go into, let me actually just do it here. Oh, I almost had a heart attack. I thought that Streamlabs was not on the proper screen, but I knew it was, but I don't know why I didn't. Okay. We're okay. So in main, let's just go ahead and recreate this graph here. So we'll have a graph G is equal to graph new, and we will have 7, or we'll just have it as adjacency matrix, and it will have 7 nodes. So let's add our edges. So graph add directed weighted edge, reference to G from 0 to 1 with weight 6. And I'm just going to do this a bunch just for all the edges here. 0 to 3 with weight 5. 1 to 2 with weight 7. 1 to 3 with weight 3. 2 to 4 with weight 15. 2 to 5 with weight 7. Right? Yeah, and then 3 to 2 with weight 2. 3 to 4 with weight 11. And then 4 to 6 with weight 3. 5 to 4 with weight 1. And 5 to 6 with weight 6. Alright, so let's just go ahead and print this out. Just so I know what I'm looking at, just to make sure this is all right. So we can just use graph toString, reference to G, and then just printf. Alright, please, no errors. What happened? Too few argument. Oh, attach index map. I forgot. Attach index map takes in another argument. Just pass it as 0, which is once again the size of the array. We just pass in 0 to set it to the size of the heap, which is all we need. We don't need any more. Alright, what else? Oh, we need to include limits for the integer max. So when we set integer max, we don't have the include there, so that's just a simple include limits.h. Like that. Now run this. Please work. Oh, God. Okay. One more thing. We need to add mheap.c to the build path. So lib/mheap.c. Just make sure to add that to the build path whenever you compile and run. Once again, if you're smart, not unlike me, and you like actually use an IDE for this, they will automatically do that. But if you forgot to, what happened? Oh, it's minheap. All right. God damn it. Alright, so let me just make sure this is all right and we have all our edges. 0 to 1, 6, 0 to 3, 5, 1 to 2, 7, 1 to 3, 3, 2 to 4, 15, 2 to 5, that should be a 2 to 5 with weight 2. 2 to 5 with weight 2. Just misread. Then 3 to 2 with weight 2, 3 to 4 with weight 11, 4 to 6 with weight 3, 5 to 4 with 1, 5 to 6 with 6. Alright, now let's go to our array here. So integer pointer p is equal to graph Dijkstra on graph G starting at source 0. Then we want to print this array. So print integer array the array P, and there will be G dot N elements in there, and then we can free P, and then call graph free on a reference to G. All right, this should be G dot N there. Please work. All right, so we have a 0, 0, 3, 0, 5, 2, 4. Fuck yes, that's exactly right. And that is Dijkstra's algorithm for you. So once again, this parents array. If you want to find the shortest path, doesn't matter the shortest path. I could be wrong, but oh yeah, no, this only applies when you start it at 0. Yeah, so this is only for 0. A source is 0 at least. So the shortest path from 1 to not from 1 to the shortest path from 0 to 4, we'll just track this back. So look at the predecessor of 4, which is 5. Predecessor of 5 is 2. Predecessor of 2 is 3. Predecessor of 3 is 0. Predecessor of 0 is 0, which is the source, and that is our shortest path. 0, 3, 5, 2, 0, 3, 2, 5, 4. So yeah, that is Dijkstra's algorithm for you. Once again, I will be posting updates about OpenGL, but I need to sit down at some point and just write some code. But I have been extremely busy lately, and also just I need to relax for a little bit. Don't want to get too burnt out because I love doing this. But yeah, so that's Dijkstra's algorithm. I got nothing else for you guys. Hope you guys enjoyed. We will, if we do some more of this, I think we might be looking at the Ford-Fulkerson algorithm next, or something else. I don't know. But yeah, that is all I have for you guys today. Hope you guys enjoyed. Hope you learned something, and I will see you guys in the next one. Have a good one.